Today, in this lecture, we will study Vibronic Interactions. We have started this unit of fluorescence spectrum, fluorescence spectroscopy. Before moving to detail of fluorescence, first we will discuss about Vibronic interactions and why this is needed, how this is different than Born-Oppenheimer conditions approximations that we have discussed in the previous lectures. We will discuss the details here. This is the details what we will study in this unit, and in this lecture we are discussing the first part, that is Vibronic interaction. This we will discuss here. In the next lecture we will discuss Hertzberg theory, but this is the first one. The aim of this lecture is to give brief about Vibronic interactions. Vibronic word is made up of two words, so we will discuss it details and why it is important. Why we want to discuss significance. We will discuss significance in this lecture. Vibronic coupling. So mind these words, vibronic and coupling. We will discuss the coupling word. First is vibronic. Vibronic basically made up of two words, electronic and vibrations. Vibrations and electronic. It is made up of two words. When we couple these two, vibration and electronic, then it is called vibronic coupling. In the previous lectures, we talked about that we never believed this, that these two may couple. But in this theory, it is given that these may also couple each other, vibrations and electronic. And this is a special kind of coupling called vibronic coupling. Sometimes this is also called non-adiabatic coupling or derivative coupling. I think you are aware of this word adiabatic or non-adiabatic. In the case of adiabatic, energy transfer is possible, is not possible. And in non-adiabatic, energy transfer may be there. It's a kind of coupling of two types of spectrums in a molecule involve the interaction between electronic and nuclear vibration motion. Here they are talking about vibration of nucleus, molecules and electronic structures. So two will vibration and electronic will be coupled here in this concept. The details are very tedious, but we can learn some idea, we can get some idea with this figure. The parabolic figure gives you idea of vibrations. On these vibration levels, in this vibration level, we are analyzing different possible levels, electronic levels, and we are observing here overlapping. If the overlapping is that from the top side, the negative overlap in the middle and positive overlap on the edges, then this is called very small overlap is there. In the second case, negative overlap to the left and positive overlap to the right, this is zero overlap, almost zero, it will cancel out. or both lobes overlap at one time. This is called excellent overlap. Overlapping of wave functions, possible wave functions, gives you the idea of vibronic interactions. The behavior effect of coupling is shown here. Uncoupled potential curve shown in the left. Parabolic structure is shown, vibrations. But when we couple with the electronics, there is some behavior change here. The left is uncoupled and the right side is coupled, and with this difference here. This is observed due to coupling, addition of coupling behavior with electronic and vibrations. The term vibronic originates from combination of terms vibrational and electronic, denoting the idea that in a molecule, vibration and electronic interaction are interrelated and influence each other. The magnitude of vibration coupling reflects the degree of integration. Actually, the concept of this vibronic is indicating that vibration and electronic both are interrelated and influence each other. Can you remember? We have discussed such type of thing previously, but with different approach. Yes, I am talking about Born-Oppenheimer approximation, which is opposite to this. In theoretical chemistry, we neglect vibronic coupling and we use Born-Oppenheimer approximations. Vibronic coupling are crucial to understanding of non-adiabatic processes, especially near point of conical interactions. The direct calculation of vibronic coupling is not common due to difficulties associated with evaluation. The actual mathematics is too tough to analyze vibronic coupling, and most of the time we neglect this coupling. I think you are aware of this word neglection. We are neglecting, we know this, the coupling may be there, the answer may be there, and we are ignoring that for the sake of simplicity, for the sake of convenience. And we believe in Born-Oppenheimer approximation. What is that approximation? I will discuss in detail again in the next slide. But the Born-Oppenheimer doesn't believe in the coupling. It believes in the liberal behavior of these. So, if you want to go into detail, this is necessary. In quantum chemistry or molecular physics and molecular physics, the Born-Oppenheimer approximation is the assumption that motion of atomic nuclei and electron in a molecule can be treated separately. According to approximation, vibration, rotation, electronic all are separate each other. You can discuss this as a sum of these three. Just memorize, in the previous unit we have also discussed this. Born-Oppenheimer gives the idea to use these various vibrations, electronics or various uh, energies as a sum. The approach which is given by Born and Oppenheimer. This is approach was given in 1927 in the early period of quantum mechanics. You may be aware of this, that the quantum mechanics originated from 1920 to 1930. So this is the early period when there was no method to calculate details. So he suggested this to neglect this and calculate. Now we know this. Now we have advanced computer techniques. So we want to learn details about this coupling. This approximation is widely used in quantum chemistry to speed up the computation of molecular wave functions and other properties of large molecules. There are cases where the assumption of separate motion no longer holds, which make the approximation lose validity, but it is then often used as starting point for more refined methods. Yes, now we have many cases where separation cannot assume. So there is no validity of these condition, but it gives you an opportunity to study more in this direction. We have already discussed this, that in a molecular spectroscopy, BO approximation or Oppenheimer approximation means considering molecular energy as a sum of independent terms. These terms are of different order of magnitude, and the nuclear spin energy is so small that often we omit this. The electron energy consists of kinetic energy, inter-electronic repulsions, internuclear repulsions, electron-nuclear attractions. So we can put these plus 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 these words. This slide I have chosen to give you a lighter side of this coupling. We have used many times this word coupling. You may be aware of coupling of vibration of pendulum. Whenever you vibrate one pendulum, then couple two pendulum, it may transfer the energies, may couple the energies. One energy is transferred to another energy, and both are independent to each other. This is called coupling. We have discussed rotational vibration coupling, and here in the last we have discussed quantum coupling is also there. One is two events are coupling. Rotational vibration coupling is an example of classical coupling, but in quantum mechanics we have row vibration spectroscopy, we have vibrating coupling we are discussing here, then angular momentum coupling, when angular momentum of two types of angular momentum couple each other, or NMR coupling or J coupling. Many couplings we have discussed and we are discussing in classical as well as in quantum. Vibronic coupling describes the mixing of different electronic states as a result of small vibrations. All the many states are mixed here to give you coupling. Although many challenges or difficulties are with this idea, vibronic coupling, it is crucial to understand the non-adiabatic process, but direct evolution of vibronic coupling has been limited. Evaluation of vibronic coupling is often associated with severe difficulties in mathematical formulation and program implementation. As a result, The algorithm to evaluate vibration coupling are not yet implemented in many quantum chemistry program suites. Still, we are using old versions. The reason for this is difficulty in mathematical formulation and programs. You might know, even with the older versions, long time may be taken by the computers to solve the problems, solve the calculations. If you add this, this will create new problems. So this is a challenge for us. The evaluation of vibronic coupling also require correct description of at least two electronic states in region where they are strongly coupled. And this require the use of multi-reference method such as MCSCF or MRCI, which are completely demanding and delicate quantum chemical methods. Now, next thing is this is further complicated by the fact the definition of vibronic coupling require electronic wave functions. Unfortunately, wave function based are usually too expensive for larger system, and popular method for larger systems such as density DFT, density function theory, and molecular mechanics cannot generate wave function information. As a result, direct evaluation of vibronic coupling are mostly limited to very small molecules. The magnitude of vibronic coupling is often introduced as empirical parameters. Ultimately, this shows our limitations. We are using quantum mechanics or Schrodinger equations, and the analysis is too difficult to work with. If you can do this, its methods are too costly. We can avoid use of derivative coupling by switch from adiabatic to diabatic representation of potential energy curve. Although rigorous validation of diabatic representation require knowledge of vibronic coupling, it is often possible to construct such diabatic representation by referencing the continuity of physical quantities such as dipole moment, charge distribution of orbit occupations. However, such construction require detailed knowledge of molecular system and introduce significant arbitrariness. Diabatic representations construct with different methods can yield different results, and the reliability of results relies in discretion of the researcher. So these are the alternates we can take. Here, some interesting facts are given for vibronic. I have discussed in 1927, Bornheimer had given the Born-Oppenheimer approximation. And the earliest example of the importance of vibronic coupling was found in 1930. So, very interesting. Within 3 years of by giving approximation, somebody raised this issue, importance of vibronic. But till today, after about 90 years, we are not having details. Even today, we are saying it is difficult to calculate. Renner wrote about the vibronic coupling in electronically excited pi state in CO2 and calculation of the lower excited levels of benzene by Sklar in 37 with the valence band method, and again in 38 by Goppert, Mayer and Sklar use MO method demonstrated correspondence between theoretical predictions and experimental results. The benzene spectrum was the first qualitative computation of the efficiency of vibrations at inducing intensity absorption. So this is the small brief of vibronic interactions and who first did this, just what are the limitations, why Von Oppenheimer suggested something, but within 3 years of Von Oppenheimer, they have raised this issue. Interesting. The Vibronic approach is regarded as a new concept that enlarges essentially the structural property bridge in physics and chemistry, and it is much more general and more adequate to the phenomena that reflect under consideration. So it is very interesting. Even today I am saying it is a new concept because the work in this direction is very small. Now again see these simulations. These two vibration states are shown here, V prime and V double prime, and various levels in V prime and V double prime, but from 0 to 6 and 0 to 6 both. Now these two behaving as two electronic states E0 and E1, and the energy transfer may take from one to another. These loops are there. It is showing you the possibility of electron probability and how electron can move from one to another. Transitions are shown here. Obviously, where these loops are maximum value, the probability of finding particle is more. And for example, E is equal to in E is equal to E0 में vibration level V0, the probability of electron is in the center, but for nu is equal to 1, the probability is away from the center, not at the center, probability is 0. So we have used many concepts here to analyze. In this lecture, we have studied the vibronic spectra, vibronic interactions, vibronic coupling. It can be asked in an exam as a short note, what is vibronic coupling, what is the meaning of vibronic, what is vibronic coupling. If we use the vibronic coupling, then what will happen to the system? Why we are not using? What is the alternate of vibronic? Means what we are using? We are using one Oppenheimer example approximation. What are the challenges and where is the hope can be used?